Welcome, everyone. Ready to dive in. Today, we're tackling signals and systems. Think of it like the hidden language of, well, practically everything.
Absolutely. It's the magic behind how things change, interact your phone, music, even heartbeats. It's all signals and systems jamming together.
And you've been neck deep in some serious university-level lecture notes on this, right? Chapters 1 through 5, the real deal.
That's right.
So we're going to break those down, hopefully, find some of those aha moments along the way. What do you say?
Let's do it. We'll unpack those dense concepts, make them a bit less intimidating.
Music to my ears. Let's kick things off with the stars of the show, signals. We're swimming in them constantly. But what makes them so important, especially in, say, engineering?
Imagine trying to get a message across. You could write it down, shout it, maybe even use smoke signals, right?
Okay, I'm picturing it.
Yeah. Each of those carries the message, but in a different form. That's a signal.
So it's not just about what you're saying, but how you're saying it.
Exactly. In engineering, those signals are often things like voltage changes in a circuit. Those sound waves hitting your microphone right now, even the pixels making up an image on your screen, they're all carrying information, just in different outfits.
Okay, that makes sense. Now, your lecture notes get into different types of signals, continuous versus discrete. What's the difference there? I always get those mixed up.
All right, think about tracking the temperature throughout the day. It changes smoothly, has a value at every single point in time, right? That's continuous, smooth, and unbroken.
Okay, so if temperature is our continuous signal superstar, what would be a good example of a discrete one then?
How about keeping an eye on the stock market, but you only check the price once a day at closing?
Okay, yeah. You get that specific value for that moment, but nothing in between those checks. That's discrete. It exists only at specific points. Ah, so it's like snapshots versus a continuous video feed? Kind of. You got it. Makes sense. But wait, there's more, isn't there? The notes also mention periodic and aperiodic signals, more signal jargon.
Not jargon, but definitely more ways we categorize these signals to make sense of them. A periodic signal that's like that friend who calls you back exactly every 2 hours, like clockwork. Repeating pattern, totally predictable.
Hopefully a bit more spaced out than every 2 hours.
Right, of course.
So our heartbeat would be a periodic signal then.
Bingo. That steady rhythm, repeating predictably, that's the key. Now, aperiodic signals are a bit more, let's say, free-spirited. They do their own thing.
Free-spirited, does that mean my random sneezing fits throughout the day are aperiodic signals then?
Exactly. Just like with continuous versus discrete, knowing what you're dealing with helps you choose the right tools to analyze them. It's like speaking the right language for the job.
Makes sense, got to speak their language, we've got our signals all sorted out, but they don't just exist in a void, do they? That's where systems come into play, right?
100%. A signal might be the message, but the system is the messenger, the interpreter, the one passing things along or changing them along the way. It takes that signal and does something with it.
Okay, so if sending a text message is like our signal, what would the system be in that scenario?
Think of the system as your phone itself. It takes your message, translates it into those electrical signals, beams it across a network, then decodes it back into readable text on the other side.
Wow, I never thought of it that way. So those Instagram filters I'm obsessed with, they're basically systems messing with the light signals coming from my phone's camera.
You got it. And just like with signals, we can categorize systems based on what they do, how they behave, helps us understand what we can do with them, right? We categorize them, figure out their quirks. Your lecture notes, they dive into some key characteristics, things like memory, causality, linearity, time invariance.
Whoa, hold on, those are some big words, like back in university all over again. Maybe we could unpack those one by one, starting with memory. So can systems actually, like, remember things?
In a way, yeah. A system with memory, it considers those past signals when it's figuring out its output. It's like imagine a bank account, right?
Okay, I'm with you.
The balance, it's not just about your latest deposit. It's the history of all your financial decisions, the good, the bad, and the ugly.
Okay, so my questionable online shopping habits, those are like signals being fed into the system of my bank account. And yeah, it's got a great memory, never forgets a late fee. What about a system without memory then? What would be a good example of that?
Picture a simple light switch. It's either on or off, right there in the moment, no lingering effects from past flicks.
So it's living in the now, only cares about the present moment. Makes sense. All right, causality. That one sounds kind of sci-fi, to be honest.
Not quite time travel or anything, but it does involve time, the order of things, causal system, the output. It only depends on past and present inputs. Plays by the rules of time, just like us.
So no building a system that predicts lottery numbers then. Bummer.
Not unless we've got a time machine tucked away in the circuitry somewhere. But honestly, pretty much everything around us, it behaves causally. I mean, your car's brakes, they don't engage before you hit the pedal.
Okay, good point. That would be terrifying. All right, let's try to tackle linearity. This one always kind of makes my head spin.
It's not as complicated as it sounds. Linearity just means a system behaves predictably. You double the input, you double the output. Simple.
So if I whisper into a linear system and I get a quiet hum, shouting would give me a much louder hum.
Precisely. Now, a nonlinear system, that might be a different story. Whisper might cause a chirp, a shout, a low rumble, who knows?
Okay, so nonlinear systems, those are the unpredictable friends in the signal world.
Got it.
What about time invariance then? What does that even mean, invariant?
Think of that friend, always gives the same great advice year after year, totally consistent. That's your time invariant system. Its behavior, it stays the same over time.
So it would process a signal the same way on a Monday as a Friday? No weekend mood swings for this system.
Exactly. A time variant system, on the other hand, that might have different outputs depending on the time of day, week, who knows. Like that friend who's grumpy before their coffee.
Been there. Okay, we decoded those system classifications, but how do we actually do anything with these signals? Like, how do we use them?
That's where those signal operations come in, right? The lecture notes mention some important ones: time scaling, time shifting, signal arithmetic. Those are the tools let us manipulate, mold these signals however we need.
Oh, like editing software, but for signals. Tell me more. What can we do with this time scaling thing?
All right, imagine listening to a podcast. But you can speed it up, slow it down, no chipmunk voices, everything's still clear. That's time scaling.
So if we wanted to make me sound super smart on this podcast, we could just time compress my voice, make me talk really fast?
You could try, but really time scaling, it's huge in image processing, resizing images without making everything look all distorted.
Wait, so that resize function I use in photo editing, that's actually time scaling in action. Mind blown. Okay, what about time shifting? Are we talking actual time travel here?
Not quite time travel, but we are shifting that signal through time. Think rewind, fast forward on a recording you're delaying or advancing the signal.
So if we wanted to make a blooper reel for this podcast, we could use time shifting to, like, line up all our funniest mess-ups.
Exactly. But beyond podcasting, time shifting is crucial in things like telecommunications, keeping those signals synced up, even with transmission delays and all that.
Makes sense. All right, last but not least, signal arithmetic. Are we literally adding and subtracting signals like their numbers?
You bet. Just like you can add sounds together to make them louder, subtract noise from a recording, we can do math on entire signals. Pretty cool, right?
So when I crank up the bass on my stereo, I'm essentially multiplying that signal. I'm a signal mathematician.
You're a natural. And think about those noise-canceling headphones they're using. Signal arithmetic, capturing ambient noise, subtracting it out, leaving you with pure bliss.
This is all starting to click now. Signals carrying information, systems processing them, operations to manipulate them, like digital Play-Doh. But something tells me we're just scratching the surface here.
Oh, you have no idea. We haven't even gotten to the heavy hitters yet. Convolution, Fourier series, Laplace transforms, those are game changers.
Okay, I'm both terrified and incredibly intrigued. But first, quick word from our sponsors.
All right, I'm back and ready to tackle those heavy hitters you mentioned before the break. Convolution, Fourier series, transforms. My lecture notes look like a foreign language trying to explain those.
We'll translate them, don't worry. Let's start with convolution sounds scary, but it's actually kind of elegant once you get it.
My notes, they call it blending signals over time. Honestly, not much clearer.
Okay, fair enough. How about this picture? That classic movie scene, someone shouts in a canyon, their voice echoes back, all distorted and drawn out.
Yeah, I get it.
That's convolution. The original sound, it's blending with all these delayed versions of itself, making that echoing effect. So convolution, it's like a blender, but for signals, mixing them up over time.
Exactly. You're the chef, but instead of ingredients, it's signals. Convolution takes one signal, kind of smears it over time based on the shape of the other one.
Okay, I can picture that, like those abstract paintings where the colors blend into each other.
Exactly. Now, technically speaking, convolution helps us understand how a system responds to a signal over time. Remember, impulse response.
Vaguely. It's like when I bump my microphone and get that awful spike in the recording.
Bingo. Impulse response, it's like the system's ID card, shows how it reacts to a sudden jolt. Convolution takes that ID card, uses it to figure out how the system will shape any signal you throw at it.
Makes sense. My notes had those diagrams, rectangular pulses, shifting and overlapping. Is that part of this whole convolution thing?
You got it. That whole fold, shift, multiply, integrate thing. Sounds complicated, but it's just a step-by-step way to visualize how those signals are blending together.
Right. Flipping one signal, sliding it along, multiplying here, adding there. Like signal choreography.
And the output signal, that's the grand finale. Convolution, it's not just theoretical, it's used everywhere, cleaning up blurry images, making your headphones sound amazing.
All right, convolution, you're officially less intimidating. But now we got to face the Fourier series. My notes say it's all about breaking down complex signals into simple sine waves. Is that right?
You're getting it. Think of the Fourier series as like a musical decoder ring. You can take any periodic signal, even something super complex like a whole musical chord, and break it down into its individual notes, which are just simple sine waves.
So it's like taking a symphony orchestra and separating out what each instrument is playing.
Exactly. And the Fourier series, it goes even further. It tells us not just which notes or frequencies are there, but also how loud they are and when they're played, like a musical score.
Whoa, okay. My notes also mentioned something about amplitude and phase spectra. Are those like sheet music for signals then?
You could say that. They're how we visualize the Fourier series. The amplitude spectrum shows how strong each frequency is. Imagine a bar graph. Each bar is a different note. The height shows how loud it is.
So a high-pitched whistle would have a tall bar way over on the high-frequency end of the spectrum.
You got it. And the phase spectrum tells us the timing of each frequency component, how they line up with each other.
Okay, I think I'm following. The Fourier series, it's like taking this messy signal and organizing it into a nice spreadsheet of frequencies.
And that spreadsheet, it's a goldmine. Engineers use it for all sorts of things, designing filters, compressing data, even analyzing the vibrations in a bridge to make sure it's safe.
Wow, that's incredible. But wait, there's a Fourier transform too, right? Is that like the Fourier series cooler older sibling or something?
Kinda. See, the Fourier series, it's awesome for periodic signals, the ones that repeat. But what about the signals that don't play by those rules?
You mean like those aperiodic free-spirited signals we talked about?
Exactly. Speech, music, the stock market, they're all constantly changing, no nice repeating pattern. And that's where the Fourier transform comes in. It can handle those unruly signals and still tell us their frequency secrets.
So it's like the ultimate decoder ring for signals. But wait, there's even more. What about this Laplace transform I keep hearing about?
Ah, the Laplace transform. It's a favorite tool for electrical engineers, like a mathematical toolbox made for circuits.
My notes mention circuit analysis and transfer functions. What are those in plain English?
Imagine trying to understand how water flows through a complicated network of pipes. Circuit analysis is like that, but for electricity flowing through a circuit, the Laplace transform, it gives us the tools to solve those electrical puzzles.
And transfer functions, they always sounded so abstract to me. What's the deal with those?
Think of the transfer function as a circuit's DNA. It tells you how the circuit responds to different frequencies, its own unique fingerprint.
So if I wanted to design a filter, like for noise cancellation, I'd need to understand that circuit's transfer function.
You got it. The Laplace transform helps us understand and manipulate those transfer functions so we can design all sorts of incredible gadgets.
We've covered so much today, from basic signals to mind-bending transforms. I feel like I've leveled up my understanding.
That's what's so cool about signals and systems. It's this hidden language behind so much of our world. Once you start to see the patterns, you'll never look at a sound wave, a circuit board, or even a stock market craft the same way again.
So true. A huge thank you to our expert for breaking it all down, and to all of you listening, thanks for sticking with us on this deep dive. Until next time, keep those signals flowing.